was looking at one of the questions for the homework we were going to do in class, and it talked about something called the Russell paradox.
Yeah. So we're gonna play with that, and we're definitely gonna have some discussions about it. So I'll defer that until we get there. Yeah.
Can you go a little bit more in depth on universal sets?
Oh, sure. Yeah, I seem to have skimped over those for some reason. So let's say that we're using set builder notation. I'm going to assume that's going to turn on in a second. Or maybe not. And this has not been my technology day. It's like I offended the technology beings or something. Oh, there we go. Okay. I just had to like acknowledge my faults. There we go. So let's say we're using set builder notation where S is the set of all x such that x squared is equal to 4. And I want to know what the elements of S are. I want to list them. Well, what are the elements of S? What do you think? 2 and minus 2. That's probably correct, unless I meant that x has to be a positive number. In which case, this is a representation of the set 2. Or maybe I have a set T equals the set of all x such that x squared is equal to 2. And what are the elements of T?
The square root of 2?
Possibly. If I'm allowed to use real numbers, square root of 2 is inside T. And the negative square root of 2 is inside T. But if I'm working over integers, there's nothing inside T. This is the empty set. So in a lot of cases, when we specify a set using set builder notation, or we talk about a theorem where we're using variables like x, we need to know what are the possible values. Okay, so the universal set, which is just this funny script U, equals the set of all possible values, or all possible elements. So it's sort of the whole space over which we're working. And a lot of times we don't bother explicitly saying what the universe is, but sometimes it's really important. Are we talking about integers, real numbers? Are we talking about animals? Or are we talking about sets? You got to know what the stuff is that you can pick objects from.
Yeah, you set it equal to an empty set, so that's different than an empty set being inside of that?
That's definitely different. An empty set and a set containing the empty set are not the same thing.
In that case, it just be equal to an empty set.
Yeah, so an empty set we sometimes write as just a pair of brackets with nothing inside, and that's just a different symbol for that. But a pair of brackets with an empty set inside is a set that has one object, right? There's the object inside. So this has a cardinality of 1, this has a cardinality of 0, so they're definitely not the same.
So you could have like a just set that's like just 2 in an empty set, like empty sets that sound always by themselves.
Say it again?
Well, I guess it kind of related to the homework.
Mm-hmm.
We'll probably go over. I was being confused with how it's. I don't know. I'll go over it.
Okay, well, we're gonna do the homework on the
Yeah,
board,
that's
so,
what I'm saying, yeah,
but we could have a set like containing the numbers 2 and the letter x and the empty set.
That's basically what I was.
That's perfectly valid. It's a set containing 3 objects. So the universal set, or the universe, is just a collection of things we get to pick from. Here, I'll push this one more just for completeness. Suppose W equals the set of all x, such that x squared equals minus 1. All right, so there's an example where the universe really makes a big difference, because if we're working over integers, this is the empty set. And if we're working over reals, this is the empty set. But if we're working over complex numbers, this contains 2 elements, I and minus I. So Definitely makes a difference. So other homework notes or questions? Let me pull up the homework here. So does the power set make sense?
Yeah.
Right, so you had a question Monday where you made a set and then you started listing subsets of it. What you were doing was you were building the power set, which is just a collection of all subsets of a particular set. And so questions 1 and 2 are just playing with that. 2, you're playing with it where the elements happen to be sets, but that's okay. And then 3, we're writing power sets of power sets, and 4, we're doing the same thing, starting with the empty set. And that's very straightforward to do mechanically, but it can start getting confusing if you think about it too much. So we'll try that on the board. What about these Cartesian products? Any issues there? Right, you grab something from the first set, grab something from the second set, put them together with a comma inside parentheses, that's something from the product, or the Cartesian product. So it's a new way to create new sets from old sets. All right, so let's break into groups. I didn't erase the boards, so I'll let you erase the boards. Let's break into groups and start working your way through these problems, and let's see how that plays out. And I'll pause the recording here. So a general comment on that question 8 and 9 from the first homework set, where we had these intervals that we were taking the Cartesian product of, and in some cases we had a rectangle including the edges, and in other cases we had a rectangle that excluded the edges. And it comes from taking products of these closed and open intervals. And this is actually a huge concept in mathematics. This is a branch off point to something called point set topology. And point set topology is basically abstract calculus. All the stuff you do in calculus with integrals and series and summations and all of this stuff, that's calculus of real numbers. And we can do calculus of complex numbers, complex analysis. We can do calculus of functions, that's functional analysis. Or we can do completely abstract calculus. And that's point set topology. And it all comes from this idea that this is a closed thing, it includes the boundary, and this is open, it doesn't include the boundary. So it's a real simple operation in set theory to take this Cartesian product, but it's actually a gateway to huge branches of mathematics, which is like one of my favorite topics. All right, so here's a homework question to work on, and I'd like you to write this up and turn it in on Friday on paper. So A is the set ABCD, B is the set ACEG, and this is similar to a problem you already did. Show the contents of the intersection and the union. Show the cardinality of the intersection, the union of A and B. And as you noted in your questions on the board, the cardinality of A union B is not the same as cardinality A plus cardinality B. But taking a look at these values, see if you can suggest a formula for what the cardinality of A union B should be. And think about that and see if it makes sense. And I can't remember if I actually went over that in the video or not. Hopefully I did not. I did, okay. So you got a hint in the video then. But just play with this, calculate those sets, show me the intersections, and then if you can come up with a formula, demonstrate that formula works in this case. Make sense? And I'll post this lecture video in a couple of hours, so the homework's at the end of it. That's ACEG for B and ABCD for A. All right, so Friday we'll work on question 5, which was Russell's paradox, and then we'll talk about the remaining lecture for Friday.